My name is George Bugh, and this is a video to explain spin waves. This is going to be a simplified explanation, and it's a classical explanation rather than a quantum electrodynamic explanation. And the classical explanation should be sufficient for you to develop a pretty good understanding of what spin waves are, how they work, and what kind of things you can do with spin waves. Spin waves propagate through precessing electrons within a magnetic material. So first I'm going to start by talking about the electron. The electron, or actually any particle with an electric field and the attribute of spin, will have a magnetic field associated with it due to the spin of the electric field. If you have a loop of wire and current flowing through the wire, you may already be aware that that develops a magnetic field due to the flow of current through the loop of wire. And a similar type of thing happens with just a single electron. If you have the electric field of the electron moving, it's no longer current flowing through a loop of wire, but rather the electric field itself that's rotating now. But still, it will develop a magnetic field similar to current flowing in a loop of wire. So for an electrically charged particle like the electron, there's a small magnetic dipole associated with it that runs through its spin axis with a north on one end and a south on the other, and lines of magnetic flux between the two, just as if you had a little small bar magnet. So within a magnetic material, like pure iron, for example, when all of these spins of all the electrons are pointed in a similar direction, then they develop a large macroscopic magnetic field from all the microscopic magnetic fields of the individual electrons. Within a sample of iron, it is not every electron that develops the magnetic field associated with a magnetic material like iron. Rather, it is only the unpaired electrons shared between bonds between the atoms in an atomic lattice of the material. If you have a single atom of iron, then the electrons in the different orbitals around the nucleus of that atom will be paired up, where you will have even number of electrons in each orbital. And for each electron with its spin axis pointing in one direction, you'll have the second paired electron with its spin axis pointing in the opposite direction, such that outside of that atom the magnetic fields are neutralized by each other. However, when you have a sample quantity, larger quantity of iron atoms all bound together in an atomic lattice, then between each set of molecular bonds there will be one electron shared between bonds, so it is no longer paired with a second electron. Once you have unpaired electrons, then you have magnetic fields that are not canceled out by compensating electron spin of a paired electron. So then if you take all of those individual magnetic fields and you have them all pointing in a similar direction, then you can get a larger macroscopic magnetic field from that sample of iron. And with any magnetic material, if you have electron spin and or orbital motion that is not compensated for by equal and opposite motion of other electrons, then those magnetic fields, if all pointed in a similar direction, will make a larger magnetic field for that whole sample. So now, it is also possible to develop spin waves among these electrons within a material like this. And to explain spin waves, first let's look at how an electron reacts to changes in the direction of its spin axis orientation. If you have a single electron that's shared between atoms in a material like iron, and that electron's spin axis is pointing up and down, then that electron with spin, if acted upon by some outside electromagnetic force or magnetic field, so as to try and turn that magnetic field in a different orientation, then it will not turn directly into the direction it's pulled or pushed, but rather, since it has spin, it will react by precessing. If you have a top or a gyroscope and you tilt it so that then gravity is pulling on it, it doesn't just move straight down due to the pull of gravity, but the combined forces due to its spin and the pull on it cause it to precess around at some precession rate and precession angle due to the combined interactions of its spin and the forces acting on it to try to reorient its spin axis. So electrons within an external magnetic field would do something similar. They will precess. So within a sample of magnetic material, if you have a large group of unpaired electrons all pointing in a similar direction, and then an external magnetic field is pulling on those, trying to reorient them in some other direction, then they will precess under the influence of that external field. The frequency at which they precess is dependent on how strong the force is that's trying to pull on them. So a typical precession frequency for electrons in a magnetic material in an external magnetic field of, say, 1 Tesla would be anywhere from 3 to 10 gigahertz, or possibly even a wider range than that. So to understand spin waves, if we look at a very simple explanation, if you start off with, say, just 2 electrons that are unpaired within a material, and due to the influence of an external magnetic field, those 2 electrons are precessing, then if they precess in phase, there's a minimal amount of energy stored in the form of a compression or expansion of the magnetic fields of those 2. However, if they're precessing and one precesses faster than the next, then there'll be a compression of the magnetic field between them due to that difference in phase angle. And when I talk about precessional phase, I'm talking about as if you were looking down into the axis of precession. If this is the axis of precession pointing directly towards the camera, and you have 2 electrons precessing around together, if they're in phase, then the precession, the instantaneous position of their axis will be the same. Now, looking at it horizontally again with a spin axis or precession axis up and down, if they're precessing around like this, and one has a slightly higher frequency momentarily of precession, then its magnetic field influences the magnetic fields of the other electrons around it. And momentarily there's a compression of the magnetic field lines between them, and that has the effect of propagating along and pushing on this one, and this one temporarily speeds up. And so you have that compression wave, or a wave of change in precession frequency, that radiates along, propagates along through the precessing electrons. It's kind of like if you had a long spring, like a slinky, and you have it expanded to some extent. If you compress a few coils and let them go, then that compression wave will move along the coil. So the same thing happens with precessing electrons. That magnetic field change from the change in precession will radiate along, propagate along through the precessing electrons. So all the time, the electrons will have a magnetic field that rotates at microwave frequencies. And you can even stimulate it to precess at a greater amplitude. You can stimulate them to all precess together. And with electrons, that's called electron spin resonance, or sometimes electron paramagnetic resonance, or within a ferromagnetic material, that's called ferromagnetic resonance. So if you stimulate ferromagnetic resonance, then you will get a peak amount of absorption or radiation from a group of electrons all precessing together if you stimulate them at their natural frequency of precession, which is dependent on the field strength of the external magnetic field. If you stimulate a group of electrons to all precess more or less together, then they're also susceptible to spin waves. So you already have a whole lot of electrons all precessing around together in the microwave frequency range, and then among all of those you also have the ability to have waves of spin waves propagating through them from changes in their precession rates. These spin waves carry momentum, where these spin waves can, in other words, transfer energy from one location to another. It's like if you have a slinky again, and somewhere along the slinky you tape a little pencil that's sticking out, and over here you compress a bunch of the coils and you let them go, and that compression wave propagates through the slinky. It's going to move that pencil, and that pencil can push objects back and forth. In other words, it's doing work. And similar thing can happen with spin waves. Spin waves carry momentum, and so in other words, they carry energy at some velocity, and they're capable of performing work. So far I've given you an idealized picture of spin waves. Within a single sample of magnetic material, spin waves can propagate in all directions. They can propagate along the surface in both directions of a thin film of magnetic material, plus they can propagate into the depth of that thin film of magnetic material as well. So in making things that utilize spin waves, it is desirable to stimulate the development of coherent spin waves in just certain directions, and to minimize the propagation of spin waves in other directions. And this can be done by controlling what type of magnetic material you use, how the magnetic particles are applied to the surface that you're working with, and things like that, which I'll go into more later. The next and also important thing to understand when developing things that utilize spin wave technology is how Lenz's law applies to things that are rotating at microwave frequencies. Lenz's law is most or often used in dealing with things like motor generators. Lenz's law states, and this is just a rough explanation, not a dictionary explanation of Lenz's law, but more or less it says that when you create a current flow in something using magnetic fields, for example, if I have a permanent magnet rotor as part of a motor generator, and I spin that rotor, and so it induces current flow in the stator windings, and those stator windings are then connected to something like a resistor or a light bulb. So I spin that permanent magnet rotor, and that induces current to flow in the stator windings, and that current flows through the light bulb, and the light bulb lights up, and you're transferring energy from the work of turning that rotor to the energy that's lighting up that light bulb. So Lenz's law states that the magnetic field that develops from the stator coil windings will always be in opposition to the magnetic field that induced that current flow to begin with. So if I turn a rotor, current flows through the stator windings, it lights the light bulb, the amount of work being done, the amount of energy being expended by that light is reflected back into the field strength of the magnetic field of the stator windings, which is in opposition to the magnetic field orientation of the rotor, and so it opposes my trying to turn that rotor, such that the amount of work I'm putting into lighting that light, the amount of energy that I'm transferring, is equal to the amount of energy that's actually getting to the light bulb or anything else within that circuit that's dissipating energy in the form of heat or whatever. So now some interesting things happen when we apply Lenz's law to devices working at microwave frequencies. Lenz's law normally applies in situations where the wavelength of the rate of rotation, say I'm rotating a rotor at 1 second, 1 cycle per second, or frequency 1 hertz. The distance from the stator coil to the permanent magnet is going to be much less than the distance it takes that electromagnetic field to radiate during a time period of 1 second. So the reflected load from the amount of current the light bulb is drawing back into the rotor to affect how hard it is to turn a rotor is almost instantaneous. But now we can do the same thing in microwave frequencies, and something different will happen. If you take a single nano crystal sized magnetic particle and you cause all of its electrons to precess in phase at microwave frequencies, then it is sending out an electromagnetic field that rotates just as if I had a very small permanent magnet rotor of a motor generator. So that rotating magnetic field is capable of inducing current flow. In this case, I won't have a stator winding, but rather you can use microwave reflector antennas that are also tied to a load. Or to give an even more basic example, instead of a stator coil, a single stator coil or loop, you can imagine that you have a whole bunch of loops all around the rotor, and they're all shorted together. So it's just like one big loop with a short. So the maximum amount of current flow will be possible through that coil, which is actually not a coil anymore, but just a spherical chamber in which that single rotating field is at the center. So the maximum amount of current induced in that will reflect back magnetic fields which would normally oppose the motion of that rotating magnetic field at the center. If there's any amount of resistance to that spherical cavity, because it's not a superconductive material or whatever, then the energy dissipated in the form of heat through the resistance of that reflecting material should be reflected back and cause resistance to the motion of the magnetic field that induced that current flow. But at microwave frequencies, it takes a certain amount of time for the electromagnetic field from the rotating precessing electrons, rotating magnetic field from the precessing electrons. It takes time to reach that cavity wall, and it takes time for the induced current's magnetic field, which would normally be in opposition, to reach back to that rotating magnetic field at the center. And it is possible to obtain a size of cavity such that the time delay of the rotating magnetic field to that surface and the time delay of the reflected opposition magnetic field back to it is such that by the time it reaches back, it is already at a point in time where the rotating magnetic field is made at least 90 degrees or probably closer to 180 degrees rotation already in the orientation of its magnetic field, such that the reflected signal coming back no longer opposes that motion but rather aids that motion. Another way of looking at it is if you have a sample of ferromagnetic material, very, very small, just a single nano-sized crystal of magnetic material, and you stimulate electron pairing magnetic resonance, or I should say ferromagnetic resonance, in that material, then it's radiating out a rotating magnetic field at its precession frequency. And if I reflect that right back into it, then my reflected signal back into it can now act as the stimulating source for ferromagnetic resonance, rather than continuing to use any other external microwave antennas to stimulate that ferromagnetic resonance. I can use its own emissions to continue to stimulate it, to continue to have ferromagnetic resonance at that particular frequency, which is the natural resonant frequency as established by the field strength of an external magnetic field. Now this only works with an external magnetic field which is not strong enough to actually remagnetize that material in the opposite direction. It's there and it's establishing what the precession frequency will be, but it's not strong enough to go ahead and flip the spins of the electrons that are causing the magnetic field. Otherwise, the little sample of material would just be remagnetized in the other direction. So I want a magnetic field that sets up what the precession frequency will be, but not a magnetic field that is strong enough to remagnetize the material in the opposite direction. So, in this situation where I have electromagnetic radiation from a simulated magnetic rotor, it's simulated by using a single nanocrystal of magnetic material which is not moving macroscopically, only the individual electrons within it are moving at a common precession frequency. If that is inducing current in the resonant cavity or reflective cavity, such that it is dissipating a certain amount of energy absorbed in the form of heat lost in the resistance of that cavity, then normally that energy lost reflected back would slow down or oppose the motion of what is causing this induced current to begin with. But now, not only is heat being drawn from this and dissipated on the cavity surface, but the reflected load, which would normally remove energy from the source and require more energy to continue the motion. Now it's coming back and it's aiding the direction of precession. Still, there's energy being drawn from the system, and the energy comes from the individual electrons themselves. And to explain this further, how that can work, it's necessary to understand how all precessing electrically charged particles everywhere interact with each other. According to classical electrodynamics, anytime any electrically charged particle is precessing, it's going to have a rotating magnetic field associated with that precessional motion. And that rotating magnetic field is radiating out electromagnetic waves. And energy is to be dissipated from that precessing particle to the same degree that energy is radiating out into space in the form of electromagnetic waves. And according to classical electrodynamics, very quickly a precessing electron would radiate away all of its energy and there would be nothing left to the electron. I say that because the mass of the electron is equivalent to its energy. It's that famous equation, E equals mc squared. So all of the energy of the electron within its electric field or whatever is equivalent to the mass of the electron. If you're radiating away energy in the form of electromagnetic fields, that energy has to come from somewhere. So if you have precessing electrons, and they're radiating electromagnetic energy, not only do they radiate electromagnetic energy, but they also absorb electromagnetic energy. And in fact, all the electrically charged particles everywhere do this all the time. They're always radiating and absorbing electromagnetic energy from their precessional motions. And this radiated energy applies forces to all other precessing particles of similar type, similar precession. And these electromagnetic waves exchanged among them all tend to move them all to a common rate of precession. So, if any individual particle radiates away more energy than the rest, such that it loses angular momentum, which quantum physics says never happens. But if it could happen, according to classical electrodynamics, it should be able to happen. Then what will happen is it's going to be precessing slower than other similar particles. And as soon as that happens, then it will no longer be in phase. Its precessional motion will no longer be in phase with precessional motions of all other similar particles everywhere. And then the forces, electromagnetic field forces that develop between it and all other similar particles, will apply forces to it to make it pick up speed again, although it will never actually lose much speed at all, because it immediately absorbs whatever energy it requires to get back in harmonious precessional motion with all other particles that are exchanging electromagnetic energy with each other all the time. There's no way to measure the electromagnetic energy exchanged between two particles that are precessing in phase, because there's a minimal forces between them as long as they're precessing in phase. It's only when one slows down and the phase difference between them develops that there's energy stored between them due to that difference in phase. And then that is what applies forces between them to move them back into synchronous precessional motion. For unpaired electrons within a ferromagnetic material, the particular precession frequencies involved are established by a field strength of an external magnetic field. However, even paired electrons within all atoms precess, and the frequency of precession in that case is established by what orbital the electrons are in, and how the electromagnetic fields of the electrons interact with each other and interact with the electromagnetic fields of the nuclei, or the protons, the neutrons, and actually the quarks that make up the protons and neutrons within the nucleus of atoms. When you have paired electrons, you can have precessional and counter-precessional motion, such that external to it, the magnetic fields appear to cancel each other out. But still, you can have waves of magnetic fields radiating from their motion that affect other similar particles of other atoms, and they all share this interaction among all of them everywhere. And to explain what I mean by that, it's best to read the papers that I've written that are available. Plus, I'll be doing more videos to explain it further. So that's all for now.